Well, welcome everyone. Thank you so much for the invitation to the organizers. My name is Bergen. I'm fortunate to work with brilliant and industrious students and colleagues like these folks who contributed to the work I'll talk about today. So I want to thank Cameron Jones, James Mikhailov, Tyler Cheng, Sean Trott, and Shauna Coulson. And you will continue to see their faces throughout because they contributed to everything that I did, that I'm going to be talking about today. So suppose you want to know how language comprehension works. We might attempt to explain language behaviors by proposing language-specific mechanisms like parsing strings of words into syntactic dependencies or hierarchical structure, or by proposing language external mechanisms like access to grounded world knowledge, innate cognitive capacities or biases, or other sorts of things. For instance, suppose you take a sentence like when the vase fell on the rock, it broke. Most readers resolve the ambiguous pronoun it as referring to the vase. There are several possible explanations for this behavior. There's a linguistic one, so comprehenders might prefer noun phrases that occur early in a sentence, like the vase does in this sentence. And in order to test this, we might construct an experiment that contrasts this sentence with one that reverses the order of the noun phrases. And if comprehenders tend to resolve this pronoun once again to the vase, even though it's no longer at the beginning of the sentence, then this might demand some alternate explanation. So for example, that explanation might be that people access world knowledge in order to resolve ambiguous pronouns. That arrow ended up looking kind of funny, didn't it? Right, so this line of reasoning, which is actually representative of most widely accepted research in the field of language processing, actually omits an alternative explanation. The distributional hypothesis proposes that language knowledge and behavior derives from statistical regularities in linguistic input itself. In slogan form, you shall know a word by the company it keeps. And the basic notion, implemented decades ago in tools like LSA and HAL that we heard about earlier, and more recently in FastText and WordDebate, among others, is that words distribute more similarly are more likely to be semantically and syntactically similar. So if dog and cat occur in similar contexts, then they're more likely to be more similar to each other than either is, for example, to car. And at scale, in principle, as the theory goes, you might be able to use distribution alone to recapitulate the full range of human lexical semantic knowledge. And the distributional hypothesis got a huge boost in the last 5 years or so with the advent of large language models, which as we heard about earlier, with increased numbers of parameters and training data set sizes and processing power and pre-training, have now shown the potential not to just recapitulate lexical semantic representations and similarities and so on, but actually to approximate a variety of human processing behaviors. And because they're trained only on linguistic input, they can actually be used as a robust operationalization of the distributional hypothesis. So the distributional hypothesis, around for at least 70 years, has gained new life. So the approach that I'm going to describe today to the distributional hypothesis runs both humans and suitable LLMs, and I'll say in a moment what I mean by a suitable LLM, on a behavioral linguistic task. We've done this for neural tasks as well, but today I'm just talking about behavioral ones. And we measure how much of the systematic variance in human behavior that's driven by the independent variables we care about can be explained by the large language model. If it doesn't explain it all, if there remains systematic behavior that needs to be explained, then the model, and thus this proxy for statistical language learning, is not sufficient to explain the human behavior. And then we have to rely on those other mechanisms that we started out with in the first place. But if the large language model explains all systematic variance in human behavior, then this is a proof of a concept for the distributional hypothesis, that this behavior that we thought had to be explained by innate or embodied or grounded or other mechanisms can actually be explained by this by distribution alone, by distributional learning alone. So right. makes an appropriate model? So we've got to first of all select a model that's large enough to approximate the human behavior. As Roger said earlier, recently these models have gotten big and powerful enough to do human-like things. But for many tasks, for sort of basic level sentence processing tasks, maybe we need a smaller model. Models, though, have to be small enough to be a realistic proxy for human learning. So human brains have about 100 trillion synapses. Probably all of those aren't dedicated to any particular language processing task, so that's an upper bound. GPT-3 Classic, which we'll be talking about a lot today for a variety of reasons, has 170 billion parameters. So it is not too large to approximate the sort of storage power of a model that we might care about, of the brain, for example. It has to not have been exposed to the specific language stimuli that we're presenting, because of course we want to be testing novel behavior on novel stimuli. It has to be architecturally suited to the human task. For online language comprehension, we don't want a model that can see the future, so we're probably talking about an autoregressive model trained only on language. We might be talking about an RNN, since people are talking again more about RNNs. It has to be trained on a reasonable size of training data. Now, this is going to be a big sticking point, because humans are only estimated to be exposed to about 100 million words of data by adulthood. Maybe that's off by an order of magnitude, who knows? But even so, GPT-3 is trained on 300 billion tokens or so. And finally, the model needs to have been trained with no humans in the loop. So that means no reinforcement learning from human feedback. The reason for that is that we want to make sure that the hypothesis that we're testing is operationalized in the model, where the hypothesis is about distributional learning itself, not about training on the basis of what humans like the behavior to be after the fact. So this is going to exclude models like GPT 3.5 and 4 that have reinforcement learning from human feedback for this hypothesis. For other research questions where we care about the behavior of any model, then we might use different criteria. Okay, so in what remains, I'm going to briefly walk you through 3 applications of this approach to different phenomena, starting with affordances. So affordances are the actions that an environment makes possible for an animal. So a chair might afford sitting on for a person, or standing on, or picking up and fending off a lion with. Affordances are thought to derive from interactions between the animal and the environment, and they appear to show up in language comprehension. So consider being asked to judge the sensibility of this sentence completed with each of the 3 words below it. So Joan was camping but realized she forgot a pillow, so she grabbed a sweater and filled it with clothes. That's a word that's related to the context. And the best completion here, leaves, which is afforded, that is, leaves afford sticking in a sweater and putting your head on comfortably, versus water, which does not afford those things. So most humans agree, and I presume you probably do as well, that clothes and leaves are good, sensible completions of this, and water is not. This is often interpreted as showing that humans access grounded knowledge about the affordances of these objects during comprehension. Those are your judgments. So what we did was we wanted to see whether the distributional hypothesis could explain away this behavior. So we used scenarios from Glenberg and Robertson's original study that looked at this. We presented these to LLMs, including GPT-3 and a couple others that I'll report on in a moment. We took the probability of each word in that variable slot and computed the surprisal, which is just a log transformation of that probability. And we conducted the same task with a bunch of human participants. This is what the human participants do. So just like they did in the Glenberg and Robertson study 25 years ago, they differentially judged these stimuli to be sensible. They thought that the related ones were more sensible than the afforded ones, both of which were more sensible than the non-afforded ones, just like you did, presumably. GPT-3 showed a similar effect for the afforded versus non-afforded difference, but not for the related versus afforded difference. Now, how do we quantify exactly whether the model is explaining the same behavior that we want to understand in humans? Well, we do that by conducting a model comparison, a likelihood ratio test between models that include and don't include condition. And here's what I mean by that. If you take a bunch of predictors, the surprisal from GPT-3, from BERT and Roberta, which are other large language models, and you use them to explain human responses. So just how sensible people judge these sentences to be. You find that GPT-3's appraisal explains a little bit of the variance. Bert and Roberta explain less of the variance, and all of them explain less of the variance than just condition does. Was it afforded or not afforded? And in terms of models, what we do is we build a model that explains human sensibility in terms of the large language models appraisal and random effects and other control variables. And we compare that to a model that adds in condition, afforded versus non-afforded. And we ask, does the model that includes condition explain more of the variance in human sensibility judgments than the one that does not? And if it does, that means that there is human behavior in response to these stimuli, the afforded versus the non-afforded ones, that is not explained by the large language model appraisal. And here, all likelihood ratio tests, testing that with GPT's appraisal versus the model plus condition, BERT's appraisal versus the model plus condition, all of them are significant events. Okay. Disambiguation will be familiar to you from the beginning because it's the example that I started with. Human comprehenders seem to systematically resolve ambiguous pronouns in ways that are consistent with knowledge about objects when possible. But how do we actually know that it's an effect of physical knowledge, like physical knowledge that vases are more likely to break than whatever it was that I said that the vase was broken by? Rock, that's what it was. So what we did was we created 30 new scenarios, like when the vase fell on the rock, it broke, and when the rock fell on the vase, it broke, but with different actions and different objects. In order to quantify the effect of world knowledge, of physical knowledge on these judgments, we normed with a totally different set of participants questions about the physical plausibility of events. So we asked, if a vase fell on a rock, which would be more likely to break? And we extracted those values and calculated the averages so that we had an average judgment about the likelihood of one versus the other event happening, the rock breaking or the vase breaking. And we presented these scenarios to GPT-3 and calculated again, the surprise of the log probability of broke in the context of when the rock fell on the vase, the rock, or when the rock fell on the vase, and also the reverse orders of those two. And that gives us the model's estimated probability that the rock would be followed by broke versus the vase would be followed by broke. We also ran the study with human participants. And what you see here is human judgments on the y-axis. You see humans' probability of each noun being the one referred to by it. So is rock the one referred to by it when it broke, or is vase the one referred to by it when it broke? And on the x-axis, you see two sets of predictions. You see the predictions from the large language model in purple, and then you see the predictions on the basis of just those probabilities of the events in the human task, where humans were asked how likely is it that the vase would be the one to break. And you can see that once again, the large language model is sensitive to this distinction. You see a positive correlation here. But you also see that the human correlation is much tighter. And in fact, once again, when we do this trick of a model comparison, we find that the large language model does not explain all of the variance in human probability judgments for the sentences that is explained by the probability of the world events according to humans. I'm scrolling on the wrong device. Oh yeah, we also did an online processing version where we wanted to know, if we don't actually just explicitly ask people their judgments about these sentences, what happens? Are they automatically encoding these interpretations? And so we followed this sentence, when the vase fell and the rocket broke, with a bunch of text, including some text that was consistent or inconsistent with each of the two interpretations of it. So Jennifer darted over to the shelf and saw that the vase was still intact on the floor, or saw that the rock was still intact on the floor. If the reader believes that the vase was the one that broke, then they will be surprised when they read that the vase was still intact on the floor. That should slow reading time. So this was a self-paced reading task. In self-paced reading tasks, oftentimes you find a slowdown in processing and a slower reaction to press the button to go on to the next bit of the text, not directly on the the bit that encodes new information, but immediately following it on the critical spillover region. So that's the on the floor, a tall lamp part here. Wrong device again. When we presented this to people here on the y-axis, you see, when we presented this to GPT-3, you'll see that regardless of whether the object described the rock being intact or the vase being intact, there was no difference in the surprise, in the probability of each of these things, either for the critical region was still in the vase rock, or the spillover region was still in, the critical region was still intact, that provides that new information, or the spillover region on the floor. But when you look at humans, you do see a difference. Humans are slower to read that the vase was still intact on the floor than that the rock was still intact on the floor, which leads us to believe that even though they weren't asked to make explicit judgments about these sentences, they committed early on to that judgment. This is not something that the large language model can capture. Of course, it has no difference. Humans have a difference. And again, this model comparison, the likelihood ratio test you see there, shows a significant degree of variance still to be explained by the consistency with the physical judgments that humans have. The last phenomenon I'd like to talk about is theory of mind, or the range of phenomena that go under the rubric of theory of mind. Most neurotypical human adults show behaviors consistent with the ability to represent and reason about the mental states of others. There have been a variety of explanations for how we do this. It could result from biological endowment. Early social interactions appear to be critical to its development. It could also be driven by language exposure itself, exposure to verbs like know and believe, and so on. We conducted a linguistic false belief task, which probes one dimension of theory of mind, the ability to track the knowledge states of others. This is like a linguistic version of the Sally Ann test, if you're more familiar with that. Basically, we presented a false belief passage in which a person is present while an object is placed in a location, and then that person leaves the room or the environment while the object is moved to a new location. They come back and they are going to look for the object, and you are asked as a participant, where are they going to look for the object? Where do they think the object is? Well, if you are tracking their beliefs successfully as different from your own, you should report that they're going to look where the object was in the first place because they weren't aware of it moving to the new place. But if you're not able to do that, then you are going to think that they'll look for the object in the same place that you know the object is, which is the end location. So passing this task is evidence that you are able to track the beliefs of others as different from your own. This is contrasted with a true belief passage in which the observer is present for the object being moved to the new location. So this is like a control condition to make sure that people are actually following the task. In this case, they should say that the object will be looked for in the new location, in the end state, because the person in the room was there to see it move. So we developed a bunch of these new passages, again, so that they couldn't be in the training set for large language models. And we manipulated a bunch of linguistic variables that we can talk about later if you like, to produce 16 versions of each. We then presented these to GPT-3 and computed for each the log probability of the start location, the token encoding the start location, minus the log probability of the end location. So that gives basically a figure of how likely is the start location relative to the end location. Higher values means it is predicting that the start location is more likely to be at the end of Sean thinks the book is in the, or Sean goes to look for the book in the. We also ran this on a bunch of human participants, more than 600 of them after exclusions, so many because we wanted them to be exposed to the exact same situation that the large language model was, which is because it's initialized each time, we presented them with only one version of one passage. So this is one shot for each of these participants. And they just filled in the final blank to say where Sean would, or who the participant would look for this object. So you see here that LLMs are sensitive to belief state. Once again, like all of these experiments, large language models are sensitive to the manipulation. So it's a little bit tough to see this. So on the right-hand side, you see higher probability that the start location will be the one filled into this blank. And on the left is that the end location will be filled into the blank. And so GPT-3 shifts rightward in the false belief condition. So it is saying that that Sean will look in the starting location in the false belief condition, which is exactly consistent with what we would expect if it was able to track the beliefs of others as different from what's true, and that it's more likely to predict the end location in the true belief condition, which is correct. But this is dwarfed by the human behavior. Humans are far more likely to show this behavior, and once again, a likelihood ratio test that compares a model of regression with the predictions of the large language model versus one that includes that and also the false versus true belief condition shows that this condition of knowledge states explains additional variance. We've conducted this with a whole bunch of other theory of mind tasks, including one that looks at recursive mind reading. So your ability to track what X believes that John thinks, and so on. We've done it with a short stories task, which tests for inference about why people would say anything that they would say, and strange stories, indirect requests, scalar implicature, and others with similar results. Takeaways are that large language models show sensitivity in behavioral tasks that have previously been used as evidence of various cognitive capacities in humans. Yet, at present, LLMs still mostly fail to explain away systematic variance in human behavior. So grounding or innate biases or other mechanisms aside from statistical language prediction are still required. Thank you, Ben. Thanks so much.